Hello everyone. Now after completion of Werner's theory, we have last time discussed the limitations of Werner's theory, and now to overcome some of the limitations we'll start today with the new theory, valence bond theory. Now this theory was given by Pauling in 1931. I have mentioned some of the major postulates of this theory. The first one, this theory assumes that metal-ligand bond formed is a pure coordinate bond. That is, metal vacates some orbitals and ligand donate their lone pairs into those empty orbitals. That means a additive bond in which ligand donate electrons in the empty orbital provided by the metal. Now, depending upon the number of bonds to be formed by the ligands around the metal, metal must have the requisite number of orbitals in order to gain the electrons of the ligand, and all those orbitals should be of same energy and same shape. That can only be done after hybridization to accept the electron pair from the ligand. Next we have sometime, in order to vacate the ligands, vacate the orbitals for the ligands, metal sometime vacate its n-1 d orbitals by pairing of electrons. Some of the n-1 d orbitals are vacated by the metal, and sometime no pairing takes place and metal has to use its outer d orbitals. For example, if first series of transition elements, then it is 4 d orbitals used in this case are used by the metal. Now the first case, if inner d orbitals are used, then in case of octahedral the hybridization will be d2sp3, and in the case 2, if the outer d4d orbitals are used, then hybridization will be sp3d2. Fine. So in both the cases it will be, the shape will be octahedral, but it only that the different d orbitals are used, right? In the first case, such complexes are called inner d orbital complexes, and second case outer d orbital complexes. Fine. Then all the metal ligand bonds which are formed are of same length and same strength, because they are a result of all the orbitals provided by the metals are due to hybridization, and all the orbitals are same. So as a result of donation, all the bonds are of same length and same strength. Now in case of octahedral, we have two types of hybridization which can be shown by different metals depending upon the ligands with which they are attached. d2sp3 if inner d orbitals are used, and sp3d2 if outer orbitals are used. In case of scale planar, it is dsp2, and in case of tetrahedral it is sp3. Now let's start by taking some examples from octahedral cases. Now first we'll take up some examples for the complexes which are octahedral, that is coordination number 6 around the metal. Now before starting valence bond theory, I must tell you that valence bond theory suffers from some limitations. The different electronic arrangement shown as a result of metal ligand coordination, that is, first the magnetic behavior, that is paramagnetic nature, diamagnetic nature, or number of unpaired electrons in the complex, they must be known. If the magnetic behavior is known, only then the bonding pattern as a result of valence bond theory can be obtained, right? So this is one of the limitations, that prior explaining the bonding of any complex we must know its magnetic behavior. Only then we can explain. In some cases pairing takes place, in some cases pairing do not take place. Now let me take first example. It is octahedral complex. The first case is an example of chromium, one of the complex of chromium. Ammonia is the ligand. Ammonia, we know it's a monodentate ligand, therefore the coordination number is 6. Fine. Now before explaining from the examination point of view, I just tell you, before explaining the bonding in this complex using VBT, we must know the atomic number as well as the electronic configuration of central metal. Secondly, we should be able to calculate its oxidation state in the complex and write the configuration of that particular ion. So I always suggest that first you should write chromium atomic number we know it is 24. So the configuration is argon 3d5 4s1. We know it is one of the exceptional configuration. Fine. Now you should be able to calculate the oxidation state putting here X. Ammonia is a neutral ligand, so it is X plus 0 is equal to plus 3. So chromium present in this complex is in plus 3 oxidation state. So you should be able to write the electronic configuration of plus 3 ion. So it is argon. Electrons are to be removed from 4s first. So it will be 3d3. Fine. This is the first step, the most important step. If you write a wrong configuration or you calculate a wrong oxidation state, you will not be able to write the correct configuration. If the configuration of that particular ion is not correct, the bonding pattern, magnetic behavior, everything calculation will be wrong. Fine. Now, let's start with the first step, that is the ground state. Suppose it is only chromium 3 ion is present and ligand will approach later on, then the configuration is this. That means there are 3 electrons in the 3d orbital. This is 3d, this is 4s, 4. Fine. So 3 electrons are there. We have found experimentally that this complex is found to be paramagnetic with number of unpaired electrons equal to 3. Fine. So otherwise also, for the cases of D1, D2, D3, there will be no pairing and nature of ligand will not affect the structure. It will always be inner d orbital complex because the 2 d orbitals are always empty in this case. So whatever is the ligand, it will not affect the bonding pattern. Fine. So in this case we'll see it's a case of 3d3. These 2 orbitals are already empty. Fine. So next case will be representation of the complex. You see here, now 6 ammonia will come to metal and each ammonia will form 1 bond. So as the bond is coordinate bond, so metal has to provide 6 vacant orbitals. So we observe here 1, 2, 3, 4, 5, 6 vacant orbitals are there. But this is not the stage for combining with ammonia, right? First of all, in this case, all these 6 orbitals, this belongs to D, S and P. They are of different energies. So they have to hybridize first so that their energy as well as their shape is same. Fine. So before combining with ammonia, we have to show that hybridization. Fine. Only then electron will be accepted, because we know that all the bonds formed with ammonia are of same length and strength, which will only be possible if the orbitals accepting electrons are of same energy and same shape. Fine. So this is the pattern 3d, 4s, 4p. Now before accepting, there should be hybridization. I am showing the hybridization like this. This shows that all these orbitals, these 2d orbital, 1s and 3p orbital, all hybridize to give you 6 d2 sp3 hybridized orbitals. So there are 6 empty orbitals available. Now all of them are of same energy. So after hybridization, now you can show that 6 ammonia will donate their electrons in these orbitals. And just concise, made it concise. Otherwise we can also show another step in which all the 6 orbitals are shown which are of same energy, but I have covered with this dotted line, right? So here you can put the lone pair donated by ammonia. These are the lone pairs donated by ammonia into these empty